Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 3 in chapter number 1, so now we will discuss about the compressible gas flow in terms of parameter that involve for the compressible gas flow. Okay, first we try to look at the difference between compressible and also incompressible fluid. So under fluid categories, there are two types of fluid, which is we refer as liquid and also gas. There are two types of fluid. First, incompressible fluid, and the second one is compressible fluid. For compressible fluid, in terms of a simple definition, is any fluid when we apply pressure to its volume, the volume will change. For example, we have a piston cylinder device with certain substance with volume equal to V1. When we apply compression process to the piston, the volume of the substance inside the cylinder decrease to volume equal to V2. So for this condition, V1 is not equal to V2, so the volume change. So this condition normally referred to gas, and gas we can consider as compressible fluid. However, for incompressible fluid, in terms of simple definition, is any fluid when we apply pressure to its volume, the volume does not change. For example, a piston cylinder device with a certain substance inside the cylinder, the volume at the initial state equal to V1. When we apply compression process, the volume inside the cylinder remain same as the initial volume. So for this condition, V1 equal to V2, no volume change. So this condition normally refer to liquid. So liquid we can consider as an incompressible fluid. Okay, now we discuss about the first parameter in compressible gas flow, which is stagnation point and also stagnation state. So in terms of definition, stagnation point actually is a point in a flow field where the local velocity of the fluid is zero. This point exists at the surface of objects in the flow field where the fluid is brought to rest by the object. Okay, to understand this definition, let we look at the figures, where the figure shows the airflow stream surrounding an airfoil. So the white line actually is the smoke line, which is represent the airflow in a wind tunnel. Okay, so yellow arrow represent the direction of flow in the figures, and if we zoom in the area close to the front of the airfoil, so we'll get this I call this bigger photo at the area in front of the airfoil. So this photo or figure actually is the result that can be obtained from the simulation, where we can see a lot of arrows surrounding the airfoil. So the scale at the left side of the photo shows the magnitude of velocity, where the blue color shows the minimum velocity, the red color shows the maximum velocity of the fluid. Okay, so we can see that here for the red color arrow shows the acceleration of fluid. Okay, if you refer to the definition of the stagnation point, where the fluid velocity is equal to 0, so we can guess that, we can predict that the point will be located in the region where a lot of arrow with blue color are located. So this is the possible area where the stagnation point located. Okay, so the point where the velocity of the fluid is 0 is referred to the stagnation point. So there are two keywords for the stagnation point. First, the velocity vector must be perpendicular to the surface. So if you refer to the yellow color, shows the direction of the fluid perpendicular to the surface of the aerofoil. Okay, 90 degree to the tangent line of the aerofoil surface. The second keywords is the local velocity is equal to 0 where the fluid flow brought to rest by the front surface of the airfoil. Okay, so that's is the what I call the definition of the stagnation point. However, for stagnation state, the definition is quite similar, where the stagnation state is a state in a flowing system when the point is brought to rest. Okay, the second parameter for compressible gas flow is pressure. So there are 5 different pressure that we will discuss. First, the static pressure, which is the static pressure is the pressure that identical to normal pressure and can be identified for every point in a fluid flow field. So the static pressure is maximum at stagnation point. The second pressure, pressure number 2, we call dynamic pressure. Dynamic pressure is the difference between the stagnation pressure and the static pressure, where this kind of pressure related to the kinetic energy of fluid particles. Pressure number 3 is the total pressure. Total pressure is the sum of static pressure, dynamic pressure, and gravitational heat, which is according to the Bernoulli's equation. So these 3 pressures can be described by using simplified Bernoulli's equation after we neglect the gravitational heat terms, which is P rho gz terms. Okay, so this is the simplified Bernoulli equation. So we have 3 terms in the simplified Bernoulli equation. For the first term, P is represent the static pressure. The second terms, half rho c square, represent the dynamic pressure, and P total represent the total pressure. Total pressure actually same as the stagnation pressure, where the definition of the stagnation pressure is the static pressure at a stagnation point in a fluid flow. So we have 4 type of pressure. So the last type of pressure, we have the total relative pressure. In terms of definition, the total relative pressure is the pressure at point where the moving gas is brought to rest with respect to the moving rotor blade. Okay, so to understand the meaning of the total relative pressure, let we look at the analogy of the total relative pressure. Let's say we have here a static rotor. The rotor doesn't move, but we have a gas flow through the static rotor. Let's say we put a specific sensor attached to the blade surface in order to measure the gas pressure. Okay, so with gas flow through the static rotor, the sensor will measure the stagnation or the total pressure of the gas. However, if the rotor rotate, which we consider rotating rotor, let's say the pressure still attached to the blade, and the and the sensor will follow the movement of the rotor. So at this condition, with gas flow through the rotating rotor, the rotating sensor measure the total relative pressure. So that's the difference between the total relative pressure and also the total pressure. Okay, now I would like to explain the difference between static pressure and also stagnation pressure of fluid. Okay, so let me look at this figure. So this figure actually the cross-section drawing of a pipeline. So we have the center line of the pipeline, and inside the pipe we have flowing fluid with velocity equal to c. And now we want to determine the static pressure of fluid at the center line of the pipeline, which is referred to the point number 1. So we can determine the static pressure at point number 1 by using a sensor or a gauge as shown in the figures. So from the gauge we will get direct measurement of static pressure at point number 1. Okay, so by manipulating the pressure difference equation between point number 1 and also point number 3, so we will get the formula for static pressure of the fluid at point number 1, which is referred to the static pressure at the center line of the pipeline. Okay, if we consider gauge pressure, so we'll get this equation: P1 minus P3 equal to rho G multiplied by Z1 plus Z2 and equal to rho G Z3. So P3 actually equal to atmospheric pressure. So rearrange the equation, so we will get the formula for static pressure at point number 1. Okay, P1 equal to rho G Z3 plus P3. So in order to simplify the equation, we assume that P ATM equal to 0, where we assume all the pressure is as the absolute pressure. So now we simplify the equation. P3 will become 0. So P1 equal to rho G Z3, where the P1 pressure actually same as the static pressure of fluid at point number 1, which represent the static pressure of fluid at the center line of the pipeline. Okay, now if we want to determine the stagnation pressure at the center line of the pipeline, so we need to use a gauge or a device that can brought the fluid into rest, so that the velocity of fluid at that condition will be 0, because we want to determine the stagnation pressure. So here we use L-shaped gauge, where the tip of the L-shaped gauge will make sure that the velocity at point number 4 will be 0. Okay, so now we can determine the stagnation pressure of fluid at the center line of the pipeline, which is referred to the location, the pressure at the location 4. So at this point, because the fluid velocity already brought to the rest by the tips of the L-shaped gauge, so C4 value, velocity at point number 4, will be 0. Then we manipulate the Bernoulli equation, where from the Bernoulli equation, because point number 1 and also point number 4 at the same level, so we'll get the same total pressure for P1 and also P4. So according to the Bernoulli equation, between point number 1 and also point number 4, so we'll get this equation where P1 plus rho C1 square divided by 2 equal to P4 plus rho C4 square divided by 2. So because we know that the fluid velocity at the tips of the L-shaped gauge, which is referred to the velocity at point 4, equal to 0, so the equation further will be simplified to this equation, where P1 plus rho C1 square divided by 2 equal to P4. So the final equation will get the equation for stagnation pressure of fluid or total pressure of fluid, where P4 equal to P1 plus rho C1 square divided by 2 equal to the total pressure of the fluid at the center line of the pipeline. So P4 equal to stagnation pressure or total pressure, P1 refer to static pressure of the fluid, and the third terms of the equation rho C1 square divided by 2 actually is the dynamic pressure. So now we already derive the equation for the stagnation pressure of fluid at the center line of the pipeline, which is it refer to the value of P4. Okay, next, under the compressible gas flow, we will discuss about the relations or the equation that involves with compressible gas flow. For compressible gas flow relation, based on the stagnation state, we have three equations involved. First, the equation for stagnation enthalpy H0. Second, the equation for stagnation temperature T0, and also the equation for stagnation pressure P0. So for stagnation enthalpy, H0 equal to stagnation enthalpy H0 equal to static enthalpy H plus the term for kinetic energy of the fluid, where C represent the fluid velocity. Okay, so this figure just want to show the relationship between HS and also the difference between different states. For example, state number 1 represent the static state, state 01 represents stagnation state, and state 01S represent isentropic stagnation state, which refer to the ideal process or ideal case. So if we refer to the diagram, enthalpy for 01S actually equal to enthalpy at state 01. So at any condition, the total enthalpy is constant if we refer to this diagram. Okay, next, the equation for stagnation temperature. So the basic equation for stagnation temperature actually is the stagnation enthalpy equation, where we need to substitute this equation into the stagnation enthalpy equation. So the equation that you need to substitute are the equation of enthalpy H equal to Cpt, the equation for a specific heat at constant pressure Cp equal to gamma R divided by gamma minus 1, and also the equation for Mach number, which is equal to C fluid velocity divided by velocity of the the velocity of the sound equal to C divided by square root gamma RT. Okay, gamma for ratio of specific heat, M equal to Mach number, A refer to speed of sound. Okay, then after we substitute all these three equations into the stagnation enthalpy equation, so you will get the stagnation temperature ratio equation. So T0 divided by T equal to 1 plus half multiply by gamma minus 1 times Mach number square. Okay, so next, the third equation for stagnation pressure. The basic equation actually refer to the Gibbs equation, the equation that you have learned in thermodynamic 1, where TdS equal to dH minus 1 over rho dP. So for stagnation state, ds will be 0, so we'll get new simplified equation, dH equal to 1 over rho divided by 1 over rho dP. Substitute rho with rho equal to P divided by RT, which is referred to the gas law equation. Substitute dH with dH equal to Cp dt, enthalpy equation, and Cp, so we need to substitute with Cp equation, specific heat at constant pressure equation. So we'll get the equation of dP divided by P equal to gamma divided by gamma minus 1 dt over T. So by doing the integration of the equation, so you'll get ln P equal to ln A plus gamma divided by gamma minus 1 ln T. So implement the log or ln rules, so you'll get the final equation for stagnation pressure. P0 divided by P equal to T0 divided by T power of gamma divided by gamma minus 1 equal to 1 plus gamma minus 1 divided by 2 Mach number square power of gamma divided by gamma minus 1. Okay, so to test your understanding about the topic, for part number 3, answer the question below. First, based on the equation for static and stagnation pressure, what is the main difference between these two pressures? Second, question number 2, two main keywords, state the two main keywords for a stagnation point. Number 3, why do we need to use L-shaped tube in determining the stagnation pressure? Question number 4, what is the basic equation for a stagnation temperature? Okay, so answer this question. You need to submit. You have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is given in the link. Okay, good luck. That's all for part number 3. Assalamualaikum warahmatullahi wabarakatuh.